Hey, Ashley's with us. I wonder who else we got here. Ashley, it's just you and me right now. Unmute and say hi.
Hello.
Hello. Uh, did we have 5 minutes? Did you have any questions for me?
No, not at the moment.
Okay, that's fine. Well, I'm going to write down the homework. You know, there's one due tomorrow. F13.8. Page 145. And then there's one due Saturday. And it's 1363 on page 148. The schedule has this as F 1363, but it's not. Hello, there's Nicholas. We've got two of my students now.
Good morning.
Howdy. Good to have you on board here. And so there's a mistake on the schedule. It says F 1363, but there is no F 1363 on page 148. But there's a 1363, and that's the one I wanted. That's the one I wanted. Yeah. Why don't we do one kind of like that? That might be good. Hey, we've got Stuart too, and Braxton. Yeah, they're coming on board here. Nicholas and Stuart, Ashley, Braxton. Why don't we do one similar? That'd be good. I do this one for homework, but I thought maybe we could cook. Hey, there's Ryan. Yeah, good deal. Ryan's with us. We could cook up a problem. Get different. We'll do it at 60 degrees. That would be good. Now, what I'm doing right now, for those of you that are tuned in, I'm going to do a problem kind of like your homework for tonight, only I'm going to change the angle to 60 degrees. You see, 60 is kind of down here someplace. Yeah, there you go. And see, what's going to happen, this is a 5-pound weight. and it's going to go around in a great big circle. And when it's at 60 degrees, there, I wonder if that shows up. Let me see. Yeah, that shows up pretty good. I might make it a little darker here. See, when it gets down there, the velocity doing this. The velocity, because it's kind of going in a big circle. You guys can see that. It's kind of going in a big circle. Yeah. Going in a great big circle. It's there at the 60 degrees. It's got a velocity. We're going to start from rest. And what I thought I'd do is do a problem kind of like the one on your homework. This is the one on your homework. The schedule says F 1363, but that's wrong. It's just plain old 1363. It's on page 148. And I'm going to do one like it. First thing, well, what they wanted to know is the tension in this cable here, or in this string. Well, you see, when you start out here and you drop this thing, there's no tension at all in that cable because it's not moving. It's at rest, and there's no tension there. I mean, we could spend time proving that, I guess. Maybe I should. Since it's not moving, the acceleration in the normal, if it's going to start moving, it's going to start going down, and the normal direction is going this way when it's right there. And the acceleration in the normal is v squared over. Now the problem they had in the book was 3 feet. They said this was 3 feet. And so the normal acceleration would be v squared over 3 feet. But see, there is no velocity because it starts at rest. They said it started at rest. So this would be 0. It would be 0 squared over 3. So there is no normal acceleration. However, there is tangential acceleration, gravity. It's going to start off just like you dropped a rock. But Newton's law says that the sum of the forces in the normal is equal to the mass times, well, it'd be 0 because there is no normal. And so there is no forces in the normal direction. Here's the normal direction going this way. That's your normal. Does that show up? Not very good. Let me make it bigger. And so the sum of the forces in the normal direction is 0 because it doesn't have any velocity to start off with. And so there's no tension to start off with. Okay, we got that figured out. No tension to start off with, but now when it gets down to here, there will be tension in the cable. And the way we're going to get that is We're going to write Newton's law in the tangential direction. Some of the forces in the tangential direction equals this here. But we need to put our tangential direction in there. That would be going this way. I like these unit vectors in green. There's the tangential unit vector, and there's the normal unit vector. There they are. Tangential and normal unit vector. Now, if you did the sum of the forces in the tangential direction, I tell you what you've got. You've got an mg right here. Does that show up? Yeah, it does. And you have the tension. And so on the left, you have that tension doesn't have any component in the tangential direction, but this one does. You've got mg cosine of theta. See, here's your theta. That whatever that angle is up there, call it theta. That's the same theta there. How do I know that? Because this line here is perpendicular to that line, and this line here is perpendicular to that line. Whenever you have two lines that are perpendicular, so you have something perpendicular to that one and something perpendicular to this one. See these perpendiculars? That means that this angle here has got to be equal to this angle here. Because this ray of this angle is perpendicular to that ray of that angle, and this ray of this angle is perpendicular to that ray of that angle. I probably should draw those rays different colors. See, angles have rays. See that angle that's green there? And here's an angle here that's, I'm going to draw the rays in red. Now it's a thing you learn in geometry, that if the rays of this angle are perpendicular to the rays of that angle, then the angles have to be the same. I wonder if you've ever heard that before. Let me ask somebody. Let me ask my friend Jackson. Jackson, unmute and say hi, please.
Hey.
Yeah. Jackson, have you ever heard that when you have two angles and the rays of those angles are perpendicular to the rays of the other angle, then those angles got to be equal? Have you ever heard that, Jackson?
I think so. Yeah.
Well, that's an honest answer. So this angle down here is theta. You think about that. That's worth knowing. If you don't learn anything else today, maybe you can learn that. But the sum of the forces in the tangential direction are mg cosine theta. It's a component, and it's equal to m at. Well, the m's can cancel out, algebra students. Isn't that nice? And so in general, the tangential acceleration is equal to g cosine of theta. Do I need to explain that better, or are you okay out there? Now we're going to get the velocity. All right, now here's your homework. I wrote that down for you. This is not F1363 like the schedule says. It's just plain old 1363. It's on page 148. Write that down. And now I'm going to find the velocity. Here we go. Well, what I'm doing is I'm doing a problem similar to the one on your homework that's due Saturday, only I changed the angle. I'm making it easy for you. But we have a lovely equation that goes like this. And you memorized that, or at least we studied it. What is this, September? We studied that in August, you know it? School started August 17th, and we studied that equation. And now I'm going to put in this acceleration. It's g cosine of theta ds equals v dv. I substituted the acceleration. But see that ds, guys, that ds is equal to 3 feet times d theta. What that is the arc length equation. Remember, it goes like this. S equals r theta. It's called the arc length. And you all know this equation. You all know, y'all, little Southern talk, y'all know that equation. S equals r theta. And so ds is equal to r, which in this case is 3 feet, d theta. Okay, so I'm going to put that in here. I'm going to go 3 d theta in here. So we got g cosine of theta, 3 feet, d theta equals v dv. Now we're going to do a little calculus trick. Watch, we're going to go meow, meow. And we're going to go from 0 to 60 degrees here. And we're going to go from 0 to v. Okay. And we're going to get the velocity. Here, let me make a little room here. Now, when you integrate cosine, you guys all know that. It's the sine. So it'll be 3 foot times g, which happens to be 32.2, because we're in English, senor. See, with feet, it's not meters. You don't go 9.81 meters per second squared. If you're talking about feet, it's 32.2. Okay, and then you go sine of theta. Well, in this case, it'd just be the sine of 60. I skipped a step, but if you need me to, I'll go back. And this is going to equal v squared over 2. I skipped a step. If you need me to, I'll go back. Now we can solve that for our velocity. Here goes. Well, why should I have all the fun? I'm going to shut up. Get your calculators out. And find the velocity when this ball gets down here to 60 degrees. Go for it. Okay. I wonder if anybody's got that. I'm always picking on Stuart, but he's a good sport. Stuart, did you get this plugged into your calculator? Did you get the velocity for me?
I ended up with 12.94 feet per second.
That's what I got. I got 12. I got 12.94 Good going, Stuart. Okay, now we're almost done. They wanted the tension when the angle is 60 degrees, and we're going to give it to them now. I just need a little room here to do it. Now, guys, the topic for today is the radial transverse coordinate system. We're going to get to that. This is not the radial transverse system. This is the tangential normal system, and it's a review because we've studied this already. And here's how we're going to find the tension. We're going to take the sum of the forces in the normal direction. And we know what that is. It's equal to the mass times the acceleration in the normal direction. Yeah, that's it. You know what? That's Newton's second law, isn't it? It's Newton's second law. If I can teach you guys to where you can competently use Newton's second law, I will not be a failure. But it's one thing to be able to write down Newton's second law like that, and it's another thing to actually be able to use it. Okay. Well, in the normal direction, we have two forces. I probably shouldn't have put my velocity in red. Because see, I like my forces in red. Here, let me put my forces in red. That's what I really like. We're going to put our forces in red. Here they are. You have the tension and you have mg. Those are the forces. I put them in red. And we're writing the sum of the forces in the normal direction. Oh, look, the tension is entirely in the normal direction. So we're going to have the tension there. But you see, there's a component of this weight. It would be, well, that's 5 pounds. It's negative though. See, it's going the other way. It's 5 pounds. Now, let me think. You know what? I think it's 5 pounds sine of 60 degrees. Or you could say cosine of 30 if that makes you happy. It's the same thing. Did you know the sine of 60 is equal to the cosine of 30? Yeah, you knew that. Okay, well, that's it, guys. That's the forces on the left side of your equal sign. And then you have your mass. But see, in English, senor, you got to do it in slugs. You got to take your 5 divided by 32.2 in slugs. Mass is in slugs times the acceleration. Okay. Well, now time out here. I took a walk and I've got a caterpillar on my, I don't know if you guys can see this. He looks dead, but I somehow took my dog for a little walk and I picked up a caterpillar. Let me do something with him. Oh, no, he's not moving. Okay, now back to the problem here. Trying to find this tension. Now the acceleration, we got an equation for the acceleration that we worked out. It's equal to g cosine 30. Well, g is 32.2. And the angle is 60 degrees. Hey, you know what? That 32.2 will cancel out. And now we're going to solve for the tension. Again, now we have Newton's second law. We have all the forces in the normal equals the mass times acceleration. Wait a minute. No. That's wrong. What I just did is wrong. It's dead wrong. Can anybody tell me why it's dead wrong? See, here's what's wrong. This is wrong. I want somebody to tell me why that's wrong. We'll go to one of my very best students here. Ryan, unmute and say hello.
Hello.
Yeah, hello. Ryan, I put in this acceleration and this is dead wrong, Ryan. What's wrong with it?
Is that acceleration for the normal direction?
It's supposed to be. If you're doing normal acceleration, this is supposed to be normal. Keep
So
going.
we're finding tangential, right?
No, we're finding normal. And I think she's got it. She's kind of got it. Ryan knows that there's a normal acceleration and there's a tangential acceleration, right, Ryan?
Yes.
Well, what did I do? What did I put in there?
Oh, you put the tangential when we're trying to find normal.
Yeah, this is a screw up, guys. That doesn't work. If you're doing normal, you want to have normal. So that's wrong. Well, now let's put in the tangential. Now, Ryan knows the equation for the tangential or the normal acceleration. Ryan, quote it for us. I'll write it. What is the normal acceleration, Ryan? Go for it.
V squared over 3, or
Yeah, she's got it. She's got it. It's V squared over R, which in this case is 3 feet. Yeah, proud of you, Ryan. Good going. And the thing is, we got the V. Look here. Let's put in the numbers. We've solved that. It's 12.94 feet per second. But wait a minute. Like Ryan said, you have to square it. Now I've got it correct. But I just about goofed up. Okay, I'm going to shut up and you have a minute. You got a lovely equation with only one unknown now. And I want you to find the tension in that cable when theta is 60 degrees. Go for it. Well, I got my answer. I wonder if Nicholas has got that tension yet. Nicholas, what'd you get for the tension? Earth calling Nicholas. Come in, Nicholas. Uh-oh, coffee break. Okay, well, let me pick on my other friend here. How about Mark? Hey, Mark, unmute and say hi. Mark, Earth calling Mark. Come in, Mark. Uh-oh, coffee break. Well, I keep trying. Jackson, you're not going to let me down. Unmute and say hi, Jackson.
Hey.
Yeah. Okay, now Jackson, have you got that tension yet?
Yeah, I got 12.997.
Yeah, let's just round it off, Jackson.
Yeah. 13.
We're just going to call it 13. But 13 what? 13. What's the units, Jackson?
2 pounds, right?
Yeah, there you go. Yeah, I was hoping that Jackson wouldn't say newtons. Because see, if you're doing it in English, it's pounds. Okay, I've shown you how to do that kind of problem. And your homework is the same problem. It's just that it's at 45 degrees. Now we need to talk about the radial transverse system. Unless there's a comment or question, I'm going to erase this. Anybody have a comment or question? Okay, well, let me erase all this stuff. And we're going to do the radial transverse coordinate system now. Newton's second law. Now there's a common name for this coordinate system, and you guys have studied it for a couple of years, several years, I bet. Somebody tell us, what is the popular common name for this coordinate system? They didn't teach you radial transverse. What did they teach you? I think I'm going to sneeze. I have that feeling. Ever get that feeling? I could be wrong, but I have a feeling I'm going to sneeze. Come on now, you guys all know that they didn't teach you radial transverse in school. What did they teach you? Let's call on my friend here, Ashley. What did they call this coordinate system, this r theta thing, Ashley?
Polar.
Yeah, that's right. It's just the polar. That's all it is. It's the polar, and you remember how that goes. The polar, they have a XY axis here, and they have a body here at an angle theta. And it's at some distance r, and here's a mass, let's say. And theta is always measured counterclockwise. Do you remember that? The angle is always measured counterclockwise. Yeah. Okay. So I thought we'd do a problem. This is problem 13105, and it's in the polar coordinates, or we know it as radial transverse coordinates. And this is 13105. Now let me find it here. 13105. Just a minute, I'm digging around here, trying to find it. Getting closer. There it is. Okay. The particle, this is on page 162. I wonder if I could get a dry eraser marker that's darker. Let me see here. Let me try this one. Maybe this one's better. Okay, now they said the particle has a mass of 0.5 kilograms. So we're on page 162. And it's confined to move along smooth horizontal slot due to the rotational blah, blah, blah. Determine the force on the rod, on the particle, normal force on the slot. Gosh, this looks hard. the rod is rotating constant angular velocity. Assume the point of contact's only one side of the slot at any instant. Well, here, let's draw the picture, shall we? Now, they gave us an angle of 30, so we could actually we could draw a 30. Let's see if we can here. All right, we're gonna draw a 30. Hey, look at that. Oh, that does better. See, I got me a new one here, and 30. We're gonna put 30 in here. All right, here goes. We're gonna put 30 in here. All right, 30 is right here. There we go. And 30. All right, here comes 30. Okay, and then so what? Well, there's a ball here. Let me do this now. There's this ball right here. Yeah, and I'm going to change this just a little bit because I don't like the way they've got their angle. See, they said this is 30. I don't disagree with the 30. I measured it, in fact, but they're saying their angle is going clockwise. Well, in the polar or the radial transverse coordinate system, that angle is supposed to be counterclockwise. You know that. Angles are counterclockwise, not clockwise. So I'm just going to change it a little bit. I don't think it'll make any difference. We're going to say the angle is here. And see, I've got it going, counterclockwise now. Well, that's still going to be 30. And see, that'll make this one 60. See, the angle here would be 60. Counterclockwise. Okay, and they said that this is 0.5 meters. Let me make a note of that. This is 0.5 meters. Okay, 0.5 meters. We're not doing English, senor. We're doing System International. We're doing meters. 0.5, it's 0.5 meters. Well, actually, they're going to go up here to the middle of the ball. There's what they're doing, which is fine. 0.5 meters. We're going to call this R. That's a nice name for it. Well, we got an R. You know what? That R is the position vector. It's the distance from the origin. So you call this X and Y. Well, there's your R right there. It's the position vector. Yeah. What else do we need to know? Oh, they said that the theta dot is 2 radians per second. This rod here is rotating clockwise at 2 radians per second. Isn't that what they said? But see, if we define the theta the way you're supposed to, then the theta dot would be a negative 2 radians per second. You all understand it's a negative because it's not going that way, it's going to the right. And if you define your angle the way you're supposed to with the radial transverse system, it's a minus 2 radians per second. So we got our theta dot. Now, what do they want us to do? Let me read this. Oh, they want all the forces on the rod. Okay, well, we can do that. It's a half a kilogram. Is that what they said? It's a 0.5 kilogram. Now I'm going to get out my red colors here. And we're going to start putting forces on here. Now here's a force right here. What's 0.5 times 9.81? It's 4.905. There's a 4.905 Newton force. That's just a gravity. And then there's a normal force of the I don't know what to call it. We'll call it eta, that Greek letter eta, okay? There's a normal force of the track. What is it, some kind of a track? Is that what they call it? The slot? It's the smooth horizontal slot. It's going up. Now, because of this rod pushing on it, I think that this normal force here is probably a little bigger than the 4.905. Does that make sense? Because see, that rod is pushing on it. In fact, here's a force here going this way. Why don't we call that F? It's pushing on it, and I think that makes this normal force a little bigger than the 4.905. Those are the three forces on the ball. And if you disagree, speak up now. I think we got all the forces on the ball. We put them in red. Actually, I think there's a little space. I probably should have drawn this. Maybe I got that ball drawn a little too big. There's a little space there between the ball and this top of this slot. Okay, well, we're doing great. Now let's see, we've drawn our sketch and we put the red stuff on there. Here, let me make a little list of things that you have to do these problems. You have to draw a free body diagram to scale. We measure your angles. We did that. And then the next step is you put forces in red. We did that. Then you put something in green. Let me call on somebody here. This is important. If you don't get this right, you'll never get the problem right. We're going to put something in green. Hey, Mark, unmute, Mark, and say hello to me. Uh-oh. Coffee break. Braxton, you won't let me down. Unmute and say hi, Braxton.
Hello.
Yeah. Hey, Braxton, I always put something in green here. It's really important. What is it? Do you know what it is?
You usually put your axes in green, like your unit vector.
Yeah, that's it. Did you say unit
Vectors?
That's it,
Yeah.
Braxton. Braxton's been listening to me. I feel better now. Sometimes I feel like nobody listens to me. Hey, Braxton, as long as I get you on the phone here, there's two of these green things. We're doing radial transverse. We're not doing normal tangential. So we need a U of R for the radial and a U of theta for the transverse. And Braxton's going to help us. Braxton, where do I, at the body now, the body's this ball here. Braxton, where do I put that U of R?
The U of R is coming directly off the position vector.
Exactly. He knows. Now, I'm just going to draw it like this. It's in the same direction as the position vector. See, there's a position vector. It's going that way. We even know the angle. It's at 60 degrees. Braxton, where do I put this? Now this one here is easy to screw up. Be careful. Where do I put this transverse unit vector, Braxton?
90 degrees clockwise of the
Oh,
radial.
it's not clockwise.
I mean counterclockwise. To
Yeah,
the left.
good
Yeah.
going. Good going.
Yeah.
Proud of you. It goes like this. There is the U sub theta. They have a fancy name for that. It's called the transverse unit vector. And then step number 4 is you do into L. One more question, Braxton. What's that stand for? Into L. What is that?
Either Newton's second law or not too late to change your major.
He's got it. Okay, well, let's do it. Here we go. Now, before we do, though, I'm going to do a little algebra or trigonometry here. A little algebra and a little trigonometry here. What I want to do is I want to get R and theta, and I want R dot and theta dot. I'm going to need these. When I do the Newton's second law, I'm going to need these. And I'll show you why. Because, see, you got to use these equations in the flap of your book. And they've got these. Now, I can get this R. Well, let me think about this. Let me write some stuff over here. Do a little trigonometry here. The sine of theta, remember I decided I'm going to use my theta down here, is the sine of theta is opposite over hypotenuse, so it's 0.5 over R, right? Yeah, that's right. Because see, here's the opposite. There's a hypotenuse. There you go. So R would be 0.5 divided by sine of theta. What do you think? Yeah, that's it. Okay, let's get the R. Go ahead, get your calculators and tell me how long R is. I've got what I think R is. What do you think it is? Somebody just go ahead and tell me.
0.577.
Yeah, that's it. Good going. 0.577 5. Hope you can read my writing. 0.5774 meters. Let me scoot that over. It's kind of in my way. Now let's get theta. Well, theta is just the 60 degrees. Now, if we need it in radians, we can always convert that. In radians, that would be pi over 3. But I think we could just use degrees. That'd be okay. Now theta dot, I know what that is. It's -2. See, this angle here is getting bigger, but our angle theta is getting smaller, so it's -2. If you want to write radians per second, that's okay with me. But see, radians are dimensionless. So it's really just seconds to the -1, you know it? It's just seconds to the -1. Okay, and theta dot, double dot. Now, guys, if theta dot is constant, if you read the problem, they said It's rotating with constant angular velocity, theta dot equals 2. Well, in our case, minus 2. What would theta double dot be? It's the derivative of a constant, right? You all understand? Do I need to explain that in calculus? The derivative of a constant is 0. Okay, we're coming right along. If we could get these, we can do this problem. Now we need r dot. That's kind of a problem. A little bit ugly, but we can do it. I just need some room here. See, we've done all this and we haven't quite got to the Newton's second laws yet. To get there, we're going to have these, all of this. But we're getting there. I just need this room here. I need the room. What we need is r dot. But see, what we have here is a quotient. When you have a quotient and you want to take the derivative of a quotient, what you have to do is you have to use the rule. Let me ask one of my students here. Let me ask my friend, see if I can find somebody I haven't bothered yet. I'll go back to Stuart. I'm always picking on Stuart. Stuart, when you have a quotient here, to find the derivative, you have to take the rule. Do you know the name of that rule, Stuart? In calculus, to take the derivative of a quotient, you have to take the rule. Uh-oh. Coffee break. Let's go to my friend Nicholas. Nicholas, if you have a quotient, how do you take the derivative of a quotient in calculus? You have to take the rule. What is that called, Nicholas?
Quotient rule?
Yeah, it's the quotient rule. Good going. I don't know if you guys remember how to do that, but what you do is you take the denominator times the derivative of your numerator, which would be 0, because the derivative of 0.5 is 0, and then you subtract the numerator, which is 0.5, times the derivative of the denominator. And what's the derivative of the sine of theta? You guys all know that. It's the cosine of theta. But now here's the dirty little secret. We're taking derivatives with respect to time, not theta. See, that dot is a derivative with respect to time. And so you have to multiply this by d theta dt, which is theta dot. We're not done yet. You have to divide by the denominator squared. Do you guys remember that quotient rule from calculus? You take the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator divided by the denominator squared. It's called the quotient rule. Okay, now let's clean this up. We know what theta dot is. It's minus 2. So what we have is a minus 2 times a minus 0.5. Well, that's just a 1. I'm getting cosine of theta divided by the sine squared of theta. How about you? I think that's right. Is that right? Yeah, because see, theta dot's minus 2 times a minus 0.5. That's just a 1. Yeah, I think that's right. We now have our r dot. Oh, dang it, I think we need the r double dot. We're going to have to do this quotient rule again, I'm afraid. Well, We didn't promise that this course was going to be easy. I don't remember promising that. So we got our R dot. Now let's do our R double dot, and then we'll be in great shape and we'll be ready to solve our problem. And now again, we got a quotient. We got a quotient here. So you have to take the denominator, which is sine squared of theta, times the derivative of the numerator. What's the derivative of the cosine? Let me
Negative
ask.
sign.
Yeah, that's right. It's the negative sign. So we could put a negative and just make that a sine cubed, couldn't we? But you got to be careful. You still have to multiply by theta dot. Because see, when you take the derivative with respect to time, we're not doing it with respect to theta, we're doing it with respect to time. You have to use the chain rule. Now I'm not done yet. Now I have to subtract the numerator, which is cosine of theta, this is ugly, times the derivative of the sine squared. We can do that. It's not that scary. We can do that. I just need the room to do it. I don't think I need these anymore. What I'm doing is I'm taking the denominator times the derivative of the numerator, and I did that, minus the numerator times the derivative of the denominator, which is going to be 2 sine of theta to the 1 power, but I'm not done yet, times the derivative of sine theta, which is cosine of theta, theta dot. You have to use the chain rule. And then you have to divide the whole dang thing by the sine to the 4th power of theta. I wonder if I did that right. I bet I did. We could clean that up just a little bit. Let's clean it up a little bit. R double dot. This is a little bit ugly. The thing is, theta dot is -2, so -2 times that is a +2. So we got 2 sine cubed of theta minus, and that's a -2. That's a minus, so that makes a plus. Doesn't that make a +4 sine theta cosine squared of theta times, well, no, that's it. Now I need to divide by the sine to the 4th of theta. Well, we need to get our numbers now. Now, R dot is cosine theta over sine squared of theta. Theta is 60. So let's go ahead and plug in 60 and see what we get for R dot. Here goes. I'm getting R dot as a whole bunch of 6's. So see, we can put that right here. Now we've got R, we've got theta, we got R dot, we got theta dot, we got theta double dot, but R double dot is this mess here. But we can do it. I'm going to plug in sine of 60 or theta of 60 here, and I'm going to solve this. Here goes. Wish me luck. Well, I'm getting R double dot is 3.849. And now we're finally ready to use our Newton's second law. We're finally ready to use our Newton's second law. Unless you have a comment or question, I'm gonna have to erase some of that to get to use our Newton's second law. Okay, nobody said anything. Here goes. I need the room here, and we've got all of our R's and R dots and R double dots and thetas and theta dot and theta double. We got all that, but I need this room. Uh-oh, I just erased something here. What was that? Does anybody know that? What was supposed to go right there? I erased something important, maybe. Anybody know what that was?
I think that was the weight going down.
Yeah. What is the weight?
4.905.
Half a kilogram? Yeah. And so you go a half a kilogram. Thank you so much. Times it's 4. This thing that I erased was 4.905 newtons. Okay, good. All right, well, let's do it. Here goes. Let's do the sum of the forces in the radial direction. You have to know where the radial direction is, and one of my wonderful students told us it's going in the same direction as your position vector. There's your position vector. See, it's going in the same direction. And now you look at the red stuff. This force here, you know what that is? That's the force of that rod that's pushing on it. That doesn't have any radial component because it's perpendicular to the radial direction. But this 4.905 does. But you know what? It's going against the radial direction. It's minus the 4.905 newtons. That angle's 30, you know it? There's a 60 here, a 60 there. That would be cosine of 30. And now this normal, that is in the positive radial direction, but it's positive eta cosine of 30. That's it, equals the mass, which is 0.5 kilograms times the acceleration in the radial direction. And we're going to get that. Because we have I need the room. Let me sacrifice this. I don't think I need that. We have an equation for that. It goes like this. The acceleration in the radial direction is equal to R double dot minus R theta dot squared. Now we better check on that. If you look in the flap of your book, did I get that right? Yeah, by Jove, that's right. Yeah, that's right. Well, see, we know all this stuff. We know R double dot, it's right here. We know R, it's right there. We know theta dot, it's right there. Plug that in. Go ahead, I'll wait for a minute. Go ahead, find the radial component of acceleration. We know all that stuff. Plug it in. Here goes. I'm going to do it. Well, I got an answer. I got an answer of 1.5394 meters a second squared. Now, if you got that, say, uh-huh.
Yep.
Yep, I heard you. Uh-huh, good going, good going. Well, you see, that's what goes right here. That's what goes right here. See why we had to do all this? Let me put it in right here. Here goes. 1.5394. Hey, you know what? We could solve for that eta. There's only one unknown in this equation. Do you see it? I'm going to shut up for a minute, and I want you to solve for this is the normal force of the slot acting on the ball. There's no friction, they said. It was a smooth slot. There's only a normal force. And that's the only unknown in this equation. This is Newton's second law in the radial direction. Do it. I'm going to do it. You do it. Let's see what happens. I got a normal force of 5.79 newtons. If you got that, say, uh-huh. All I heard was sort of a grunt.
Yeah, I get it.
Yeah, well, yeah, there's one.
Uh-huh.
There's one. There, good, excellent. Okay. Well, we found out that normal force. Now we're going to do the Newton's second law in the transverse direction. I hate to erase that, but we could always find it again. We're going to do the sum of the forces in the transverse direction. We got to know where it is. Here's the transverse direction. See it? It's going that way. Well, look at that force there. It's entirely opposite the transverse direction. So it's going to be a minus F. You know what that is? That's the force of this rod pushing on the ball. Now, I think that this weight, sorry I erased that, but I think it's going against the transverse direction. I think 0.5 times 9.81. That was the 4.905. I think we got a minus 4.905 newtons. That's what this is. That's this weight. Is it? See, we want the component. This has a component going like that. I think it's cosine of 60. Yeah. See, the component going the other way was cosine of 30. That was that component there. But this one's a cosine of 60. There's a 60-degree angle in there. Okay. And also this one here. Now this one's in the positive transverse direction, so it's plus eta. But the thing is, we know what eta is. We figured it out. It's 5.79 newtons. But see, what we need is the component going this way. You know what I think that is? I think that's a cosine of 60. I think that's it, guys. And then that's going to equal what? Well, it's going to equal the mass, which is 0.5 kilograms times the acceleration in the transverse direction. Do we know what that is? No, we don't, but we're going to find it right now. Here we go. The acceleration in the transverse direction is equal to, it's in the flap of your book, it's equal to r theta double dot plus 2r dot theta dot. Go to the flap of your book and look up the transverse component of the acceleration and see if you can find it. I'm looking. I don't see it. Oh, there it is. It's r theta double dot plus 2r dot theta dot. Yeah, that's it. Well, we can get it. We can get this transverse acceleration because we know everything. Oh, look at here. That's 0. Theta double dot 0. You can just forget that term. It's 0. And so you're going to have 2 times the 0.6666 times minus 2. Do it. Plug that in. Let's see what happens. 2 times 0.6666 times minus 2. Did you get a negative 2.6664 meters per second squared? If you did, say uh-huh.
Uh-huh.
Yeah, there's somebody. We're on board. Well, now we're gonna plug that in. See, this is minus 2.6664. Ah, now look at us. Look at us, guys. We have an equation here with only one unknown, and we can find the force of the rod pushing on that ball. There's only one unknown. Plug all that stuff in and let's get it. Go for it. It's a little bit messy, isn't it? Well, I did all that stuff, and here's what I came up with for the force of the rod pushing on the ball. I'm getting 1.776 newtons. If you got that, say uh-huh.
Yep.
There's 2 of us.
Uh-huh.
Was that another one?
Yeah, I got that.
Yeah, great. Okay, now let's look and see how we did. This was problem 13-105. Go to the back and look at the answers for 13-105. 13-105. Now, what they said for the answer book in the book, they said that this was 1.78. Hey, I'm okay with that. I think they just rounded off. 1.78 newtons is what they got. And for this other one, they got 5.79. Well, that's what we got. They got 5.79. Well, how about that? Even the blind squirrel finds a nut now and then. I would say that was hard, though, wouldn't you? A long, hard, difficult problem. And I helped you with your homework problem. That's good. Do you have any comments or questions? Well, okay. We have 8 minutes and you paid your tuition, so I'd like to use this 8 minutes to show you something. Unless somebody has a comment or question, I'm going to erase all this wonderful stuff. All right, say goodbye to that. That was fun. We did 13-105 together, didn't we? And it's all going to be on YouTube, so you can watch it over again if you wanted. Let me just sort of give you previews of coming attractions. I think we pretty well finished up our chapter 13, and we're going to enter the exciting world of chapter 14. I'll tell you a little bit about it. It's all about work and energy. You do have a homework problem. I announced those at the beginning of the lecture. But part of your homework would be to read ahead and read chapter 14. But I want to give you a little help in doing that. I'm going to give you, do they call it a glossary? It's where, how do you spell glossary? Oh, gee. Is it A-R-Y, do you think? It's where they explain some of the terms. See, you're used to the symbol for work being W. That's what I like. W, that's what it should be, but in your book, tell you what, we'll have a column here of how Griffin would do it if he was writing this book. And then we'll have a column of how the book does it. They don't call work W, they call it capital U. Kind of confusing. But not if you can have a translator like I'm providing you here. Now, there's also something called kinetic energy. I know you've heard of kinetic energy. It's, you know what it is, it's 1/2 mv squared. Yeah, that's what it is, kinetic. And if I was writing the book, I would call kinetic energy K dot E dot. Your book doesn't do that. They call it T. So the secret symbol for kinetic energy in chapter 14 for kinetic energy is the symbol T. As you read this chapter, when you see a T, they're talking about kinetic energy. Now, to be fair, there is a T in the word kinetic. See that T? There it is. Kinetic energy does have, it does have a T in it. Now let me go on. We're translating their secret terms in this chapter here. The most important equation in the chapter is called the work energy theorem, actually. Well, that's the way I learned it, but they call it the principle of work and energy. They call it the principle of work and energy. They put an and in here. Now, if I was writing that, what I would write is that the sum of all the works done on a body is equal to the change in your kinetic energy. That's how I would write the work energy theorem. But that's not how they write it. On page 186, here's how they write it. They write it like this. This is on page 186. This is how they write the principle of work and energy. The way I learned it was it's called the work and energy theorem. And there it is. That's the way Griffin would write it if I was writing the book. But you know what? It's the same thing, because if you did a little algebra here, you could take the sum of this T2 minus the sum of the T1s over on the right-hand side, and you'd have the sum of the U's on the left. Isn't that the same thing? And you know what this is? This is it's the change, the total change in your kinetic energy of your body. See, that's the final kinetic energy, and that's the initial kinetic energy. And if you subtract final minus initial, you get the change in your kinetic energy. And see that this is their secret symbol for work. See, if I wrote it, I'd say the sum of the W's, the sum of all the works done. But they go the sum of this U thing, which they call work. One last thing, and then we're going to have to quit. I'm running out of time. I'm giving you the secrets to reading this chapter, and we'll talk about it soon. Towards the end of the chapter, they get into potential energy. Now, see, if I was writing potential energy, if I was writing the book, I would write it P dot E dot. Potential energy. You might have seen that before. But that's not how they write potential energy. Believe it or not, the way they write potential energy is with a V. V is their secret symbol for potential energy. And it doesn't make a lick of sense to me, because there is no V in the word potential energy. I don't see any V's in there. Do you? There's no V in potential energy, but nevertheless, towards the end of the chapter, you'll encounter some V's That's their secret symbol for potential. It's actually gravitational potential energy. Okay, well, we've had fun. I hope you enjoyed that. Here's your chance for a last comment, because our time, it's sad, but our time together has come to an end till, when do we meet again? Next Monday at 9:30, I guess? Yeah. But in a few minutes here, a few seconds, I'm going to say goodbye. Did you have any last words? Well, can you say goodbye? I'm going to say goodbye. Goodbye, students.
But
Bye.
Bye-bye.
Bye.
Be careful. We'll see you next time.